Okay, for what we have in chapter 4, okay, we'll be looking into vectors, and I'm just going to give you a brief overview before going into topics pertaining to linear independence and linear dependence. And we have what is referred to as a vector space, and we have by definition, okay, we have says to let V be a set on which two operations, whether it be addition or between the vectors or scalar multiplication, where they are defined, and it says if the listed axioms are satisfied for every u, v, and w in V and every scalar c and d, then V is going to be a vector space. Okay, we have our various properties, and we have regarding addition where we have the sum of the vectors u plus v is in V. This is closure under addition. And we have u plus v is equal to v plus u. That's the commutative property, kind of like in pre-algebra or even algebra. We have like the commutative property a plus b is equal to b plus a. And we have the associative property where we have u plus the quantity of v plus w is equal to the quantity of u plus v followed by the addition of w. And we have with the additive identity, okay, so we have v has a zero vector 0 such that for every u in V, we have u plus 0 is equal to u. And for the additive inverse, okay, we have for every u that is in V, there is a vector in V denoted by negative u such that u plus negative u is equal to 0. And regarding scalar multiplication, okay, we have c times u is in V, and this is what is referred to as the closure under scalar multiplication. And we have with the distributive property, we have c times the quantity of u plus v is equal to cu plus cv. And we have with the distributive property as well, we have c plus d quantity times u is equal to cu plus du. And we have with the associative property, so we have c times the quantity of d times u is equal to the quantity of c times d multiplied by u. And for the scalar identity, we have 1 times u is equal to u. And we have with standard operations where we have to be a vector space where we have r to the second, and this is going to be in reference to the set of all ordered pairs of real numbers. So you have the set of all ordered pairs of real numbers. We have r to the second with the standard operations is going to be a vector space. And we have vectors in this space have the form where we have this particular case, you have via1, via2, okay, quantified in the parentheses. And we have for r of n, okay, with the standard operations, okay, that is a vector space. And we have the set of all ordered n tuples of real numbers r of n with the standard operations is going to be a vector space. And we have throughout, okay, we have vectors in the space are of the form, okay, we have v of 1 all the way out to v of n quantified. And we have for the summary of important vector spaces, okay, so you have r is referred to as the set of all real numbers, and you have r to the second, you have the set of all ordered pairs, and we have r to the third, we have the set of all ordered triples, and we have for r to the n, we have the set of all n tuples. And okay, and we have for the rest, okay, you have c alongside you have negative to positive infinity, so that is the set of all continuous functions defined on the real number line. And we have where we have a closed interval, okay, where we have a and b contained, that is the set of all continuous functions defined on a closed interval. Again, where we have between a and b, and again, a and b are not equal to each other. And we have for p, okay, this will be the set of all polynomials. And we have for p with n subscripted, okay, that is going to be the set of all polynomials of a degree less than or equal to n together with the zero polynomial. And we have for m of, and we have subscript in lowercase m, n, that's going to be the set of all m by n matrices. And for we have m of n comma n, that's going to be the set of all n by n square matrices. And okay, now where we have regarding spanning sets, and we have by definition for a spanning set of a vector space, Okay, so we have a spanning set S, and this is going to be a subset of a vector space V. And the set S is a spanning set of V when every vector in V can be written as a linear combination of vectors in S. And in such cases, it is said that S spans V. And let me give you just a case here where we have just going back to the set of all real ordered pairs. And let's say that if we have S to span R of 2, in this case, where we have, again, the set of all real ordered pairs. Okay, so if we had the S is equal to, and we'll say we have 1, 2, as well as 0, 1, and we can let U be equal to U of 1 and U of 2, and this will be any vector that we have in R2, and we're to look at finding scalars C of 1 and C of 2 such that we have that U in the form of, or in the guise of U of 1, U of 2 is equal to C of 1 V1 plus C of 2 V2, and we have in the setup, okay, so we have with V of 1, we have 1, 2, V of 2 we have with 0, 1, and looking at what we have here. So you got U of 1, U of 2 is equal to C of 1 times 1 plus C of 2 times 0. So you got C of 1 at the front. And following, we have C of 1 times 2 plus C of 2 times 1. So we have 2 times C of 1 plus C of 2. And we have mapping together. So you have C of 1 mapped with U of 1. And 2C of 1 plus C of 2 is going to be mapped with U of 2. Okay, so we have this set of equations. And for what we have in the case of the coefficient matrix A, so you got 1, 0. So you got 1 C1, but no C2 in appearance. And we have, for the second row, we have 2 in reference to 2 C of 1 and 1 in reference to C of 2. And we have for the value of the determinant, okay, that is equal to 1. And since the determinant of the coefficient matrix is non-zero, we can say that S spans the set of all real ordered pairs. Now, for, let's say we have that S consists of 3 and 4, followed by -6 and -8, and running through the same procedure. And we have this time around, we're going to have a system of equations whereupon we're going to have 3C of 1 minus 6C of 2 is equal to U of 1. And we have 4C of 1 minus 8C of 2 is equal to U of 2. And we have for the coefficient matrix, okay, again, we have 3, -6 for the top row, 4, -8 for the bottom row. And taking the value of the determinant, okay, this is going to come out equal to 0. And since the determinant of the coefficient matrix is 0, we have the S does not span what we have for the set of all real ordered pairs. Okay, so for R to the N, okay, if you have a 0 determinant, we cannot say that S is going to span. Okay, and now going back to what we have with reference to linear combinations, and for what we have in the case of a vector space, we have by definition, okay, we have a vector V, and a vector space is a linear combination of the vectors. Okay, we have U of 1, U of 2, all the way out to U of K in V, when V can be written in the form where we have V is equal to C of 1, U of 1, plus C of 2, U of 2, all the way out to C of K times U of K, where C of 1, C of 2, and C of K are all scalars. Now, just as an example here, say we were to write each vector as a linear combination of the vectors in S if possible. So if we had the S to contain 4, 2, as well as 2 and 7, and we can say that we have for the given vector W, okay, we have is equal to 3, 1, and we have with the formula, okay, so we got, so we have scalars of C of 1 and C of 2, and we're going to start out in the general case that W is equal to C of 1, V of 1, plus C of 2, V of 2, and substituting accordingly. Okay, so you got 3, 1 is equal to C of 1, V of 1 we have from S, we have 4, 2, and we have plus C of 2, V of 2, whereupon V of 2 is at 2, 7, and putting together, so you got 4C of 1 plus 2C of 2, followed by 2C of 1 plus 7C of 2, and mapping together. So we've got 4CO1 plus 2CO2 is equal to 3, and 2CO1 plus 7CO2 is equal to 1. And for this system of equations, we have with the coefficient matrix, we have 4 and 2 in the top row, 2 and 7 in the bottom row. And the value of the determinant, you're going to have 28 minus 4, which comes out to 24. Now, in looking at finding out what the scalars are going to become, we can take what we have in the system of equations and write what we have as, again, an augmented matrix. So we have, again, so you got 4, 2, 3, 2, 7, 1, and putting what we have in reduced row echelon form. So going through the process, say if I divide the first row by 4, so we have at the top 1, 1/2, 3/4, and then subtracting what I have twice the first row elements away from the second row elements. So we have 271 becomes 0, 6, negative 1/2, and nearing the reduced row echelon form. Okay, so if I divide the second row by 6, okay, so we have changing over from 0, 6, negative 1/2 to 0, 1, negative 1/12. Okay, so I have this set up, and if I make the, or arrive at where the second column consists of 0 and 1, changing the 1/2 to a 0. And this would be through the process of subtracting half of the second row from the top row. And so we have 1, 0, 19 24ths, 0, 1, negative 1/4. And so we have CO1 is equal to 19 24ths, and CO2 is equal to negative 1/12. And so we have as a linear combination, we have that 3 and 1 from W is equal to 19 24ths of 4 and 2 minus 1/12 of what we have with 2 and 7. And we have second case here, and I'm keeping the same values for W. And the change up this time is where I have an NS. Again, I still have 4, 2, but this time instead of 2, 7, I now have 2 and 1. And we have with the substitution. Okay, so we're going to have with the system of equations, we have 4C1 plus 2C2 is equal to 3. And then we have 2CO1 plus CO2 is equal to 1. And for the coefficient matrix, okay, again, I have 4 and 2, 2 and 1, and the determinant value is going to be 0. And since the determinant of the coefficient matrix is 0, there is no solution. Therefore, W cannot be written as a linear combination of vectors in S. All right, so if the determinant is non-zero, we can have a linear combination. However, if it is 0, then there is no linear combination possible. Now, for what we have regarding linear dependence and linear independence, okay, say we have for a set of vectors, okay, we have S consisting of V of 1, V of 2, all the way out to V of k in a vector space V. The vector equation becomes where we have involving the scalars. So you have C of 1, V of 1 plus C of 2, V of 2, all the way out to C of k, V of k is equal to 0. Always has the trivial solution. C of 1 is equal to 0, C of 2 is equal to 0, C of k is equal to 0. If we have that, when a non-trivial solution exists, then we're going to have the set S to be linearly dependent. And for what we have in the case of testing for linear independence and linear dependence, okay, say we have for the same set S, okay, and we have the vectors in a vector space V, and to determine whether S is linearly independent or linearly dependent, okay, consider the following. Okay, and we have first of all from the vector equation, okay, C of 1 V of 1 all the way out to adding C of k V of k equal to 0. It says to write a system of linear equations in the variables C of 1, C of 2, and C of k, and determine whether the system has a unique solution. And if the system has only the trivial solution, whereupon we have all the constants equal to 0, then you're going to have the set S to be linearly independent. However, if the system has non-trivial solutions, then what we have for S is going to be linearly dependent. All right. And we have as a case here, testing for linear independence or linear dependence. And say we have the S consists of 1 and 2 and 0 and 1. And we have, okay, so just setting to 0. So you got CO1 V of 1 plus CO2 V of 2 is equal to 0. So we got CO1 and the V of 1 is 1, 2. And plus CO2 V of 2 where V of 2 is 0, 1. And we have with the combination, so you got CO1 plus nothing and CO2 is equal to 0. So you have CO1 is equal to 0. And we have 2C of 1 plus CO2 is equal to 0. And you could just substitute it. You could have substituted and just for the augmented matrix, regardless of whether you use substitution or using matrices, it's going to have the outcome whereupon CO1 and CO2 are both 0. And we have the only solution possible is trivial, whereupon all the coefficients are automatically 0, and thereby the system is therefore going to be linearly independent. Now, let's say that if we have S to consist of 4, 2, 2, 7, 3, 5, and we have with this combination, we have C of 1 V of 1 plus C of 2 V of 2 plus C of 3 V of 3 is equal to 0, and substituting the numbers for V of 1, V of 2, and V of 3, okay, we're going to have for the system of equations. So we got 4C of 1 plus 2C of 2 plus 3C of 3 is equal to 0, and also 2C of 1 plus 7C of 2 plus 5C of 3 is equal to 0. And we have the augmented matrix is going to become where we have the top row consisting of 4, 2, 3, 0, and the bottom row consisting of 2, 7, 5, 0. And the reduced row echelon form, okay, we have to become 1, 0, 11, 24, 0. And we have 0, 1, 7, 12, and 0, whereupon we have C of 1 is equal to negative 11 24 C of 3, and C of 2 is equal to negative 7 12 of C of 3. And so for what we have going back to the initial setup, if I substitute for C of 1, what I have in terms of C of 3, okay, so we got, in this case, we have negative 11 24 C of 3, 4, 2 plus negative 7, 12, C of 3, 2, 7 plus C of 3, 3 and 5 is equal to 0. And since the solution is non-trivial, the coefficients do not all automatically equal to 0. And we have the system to therefore be linearly dependent. And just to reiterate, okay, so for this combination, anytime that there is a potential for there to be a non-zero coefficient, okay, like in the case of this last set, again, you're going to have linear dependence in this case.